Hello everyone. Today I'm here back with another interesting topic from Principles of Programming Using C, that is need of cache memory in the computer. Let's look into the topic. Introduction to cache memory. What is cache memory? Cache memory is a small high-speed memory integrated into the computer's processor. It is designed to reduce the time it takes to access data from the main memory. Cache memory stores frequently accessed data and instructions for quick recovery. Cache memory works and its benefits. When the CPU needs to access data, it first checks the cache memory. If the data is found in the cache, it is recovered from it quickly, avoiding the need to access the slower main memory. If the data is not present in the cache, it needs to be fetched from the main memory and stored in the cache for future use. What are its benefits? Improved performance, reduced latency, cost efficiency, enhanced user experience, and scalability. Improved performance. Cache memory significantly reduces the time needed to access data, resulting in faster processing speeds. Reduced latency. By storing data closer to the CPU, cache memory minimizes the latency associated with accessing data from the main memory. Lower power consumption. Cache memory allows the CPU to access data more quickly, reducing the idle time and resulting in lower power consumption. Cost efficiency. Cache memory is more expensive per unit compared to main memory, but its smaller size makes it more cost effective overall. Enhanced user experience. Faster data recovery from cache memory leads to smoother and more responsive user experiences, especially in applications that require real-time processing. Scalability. Cache memory can be scaled by increasing its size or adding multiple levels, allowing for better performance as the demands on the system grow. Faster data access. Cache memory helps improve computer performance by reducing memory latency. It can deliver data to the processor much faster than the main memory. By storing frequently accessed data closer to the processor, cache memory minimizes the time spent waiting for the data to be recovered from the main memory. Next comes the exploiting locality of reference. Programs tend to exhibit temporal and spatial locality of reference. Temporal locality refers to the tendency of programs to access the same data repeatedly over a short period. Spatial locality refers to the tendency of programs to access the data located close to the recently accessed data. Cache memory takes advantage of this property by storing data and instructions that are likely to be accessed in the near future. This helps to minimize the number of memory access required for improving overall system performance. In this slide, I'm going to explain about enhancing multi-level caches. Multi-level caches are used to improve data access speed in computer systems. Enhancements can be made to these caches to further optimize performance. Three key techniques for enhancing multi-level caches are cache coherence, cache replacement policies, and cache prefetching. So, what is cache hierarchy and cache coherency? Cache memory acts as buffer between the processor and the main memory. It creates a hierarchy of memories, with the cache being the fastest and the main memory being the slower. This memory hierarchy allows for efficient data access and utilization of available resources. Cache coherency. It refers to the consistency of data stored in different caches that access the same main memory. Cache protocols ensure that all caches have the most up-to-date version of shared data. This allows for consistent and reliable computation in a multi-core or multi-processor system. Cache related issues. There are different levels of cache memory like L1, L2 and L3. L1 cache is the closest to the processor and has the fastest access time. L2 and L3 caches are larger but slower, serving as additional layers of memory hierarchy. Cache related issues may include cache thrashing and cache pollution. Thrashing occurs when cache is constantly filled or emptied. Pollution may happen when unnecessary data is occupied in the cache space. Let's discuss about future trends in cache memory. Future cache memory is expected to have larger storage capacity, allowing for more data to be stored closer to the processor. Cache memory hierarchy is likely to become more complex, with multiple levels of cache being utilized to optimize data access and reduce latency. Future cache memory systems will focus on improving cache coherence protocols to ensure data consistency across multiple cache levels and processes. Cache replacement policies, which evolved to become more intelligent, utilizing machine learning algorithms to adaptively determine which data to evict from the cache. Future cache memory systems may integrate cache and main memory more closely, blurring the line between the two and improving overall performance. Future trends will involve programming techniques that take advantage of cache memory hierarchies and optimize data access patterns to maximize cache utilization. Non-volatile cache memory, such as phase change memory or resistive random access memory, may become more prevalent, providing fast access to the persistent data. Cache virtualization techniques will be developed to improve resource utilization and enable data efficient sharing of cache memory across multiple applications or virtual machines. The conclusion part: cache memory is a crucial component in the modern computer systems. It improves performance by reducing memory latency and boosting CPU efficiency. By storing frequently accessed data closer to processor, cache memory optimizes data access and contributes to overall system performance. Thank you.